So we're starting into electrochemistry. I have a single replacement up. And one thing I'll come back and emphasize in the future is that every single replacement is a redox reaction. There's always an exchange of electrons in single replacements. Not every chemical reaction has an exchange of electrons. Okay? Double replacements never do. So let's look at the charges of each individual piece and figure out which chemical might have gained and which might have lost. So if we start with the first zinc, that is zinc solid, that is elemental zinc by itself. Metals all by themselves have no charge. If you touch a piece of metal, you don't get electrocuted, you don't get zapped. So you have to be careful. Don't just look at zinc and go, oh, it's zinc 2+ from my table. It's by itself, it's not ionic. Okay. Then we have HCl, okay? Hydrogen and chloride. This is quite a polar bond. I'm going to treat this as it's ionic, as it would be if it was an ionic bond. Okay? Treating this very polar bond as ionic, this hydrogen would have lost the electrons and would be positive. Chloride would have gained and it would be minus. Okay. Again, a bit of an assumption there, but it really works to explain this reaction. We move to our products and we have a clear as day ionic compound with distinctive charges. We've got zinc chloride. This is where in ionic compounds you have to use your chart to figure out the charges. Okay. Zinc is written right in your booklet. It is +2. The chloride is not in your booklet. You have to realize the far right column of the halogens have no charge when they're in ions. Then it's -1, -2, -3 is their charge when they're ionized. Okay. So the group 7A or group 17 halogens are -1. Okay. So that's not diatomic chlorine, that's 2 chloride ions. Okay. Chemists are lazy, we don't like to write ones. That's why I just went minus. Last, we get to a molecule, diatomic hydrogen. So we're going to have to do a little bit of Chem 20 discussion or visual. Okay. Hydrogen has 1 electron. Okay. It has a bonding capacity of 1, so you get 1 shared bond in hydrogen. Okay. It is a non-polar molecule. So I'm trying to think of what is the charge of any of those hydrogen. These electrons are perfectly split. Each hydrogen would be neutral. So I'm going to put a neutral charge. Okay. Same, anything in its elemental form is not going to have a charge. Okay. So I wrote the charge above every species. It's not the total, it's the count for just one of them. So above Cl, I wrote a minus, but I'm saying each one of those chlorides are -1. There's 2 of them, they're -2 in total. But I'm going to very consistently throughout this whole unit, always write the charge for one of the entities that's below it. So what happened here in terms of electrons? Something you wouldn't have looked at before. Does zinc change its charge? And yes, it does. It starts with no charge and it ends up at +2. So it had to have gained or lost electrons in order to change its charge. It can't have the same count anymore. So you have to think, what's going on? Is this a gain or is this a loss? Now, electrons are negative. So if you gain electrons, you become more negative. But that's not what was happening here. This is becoming positive. So it's not gaining electrons, this is losing electrons. So I'm going to go minus electrons as a short form. Specifically, it's losing 2 electrons because 0 going to -2. Now, the electron exchange always happens in pairs. If something loses electrons, something else has to gain, and there might be species that don't gain or lose. If we look at the hydrogen, it's starting plus, and going to 0. So its charge is actually dropping. Positive is going down to 0. This is gaining electrons. Gaining something negative drops the charge. Plus 1 to 0 is 1 electron. Now, I like to emphasize that the count is for 1 of something. You don't always have to do this, but I want to go, that's loss 2 electrons per, that's my slash zinc. So every zinc is losing 2 electrons. Here, it's gaining 1 electron for every hydrogen. So I'm not referring to the pair of hydrogens gaining 1, it's each hydrogen is gaining 1. Okay. So we've kind of figured out a lot of the redox chemistry. Zinc is losing, hydrogen is gaining. If we look at the Cl, our chloride ions, they're not changing. So they're not doing any redox chemistry. So I'm going to just call those a spectator ion. Okay. Now I have a little number line hidden to try to help you with the gaining and the losing. We're going to be doing this in almost every problem, tracking what the charge is doing. So anytime you're going up in number, you're getting more positive. Okay? Could be -1 to 0, -1 to +1, okay? -2 up to -1. Let's think of what that is doing in terms of electrons. Well, if you're becoming positive, you can't be gaining electrons, you must be losing electrons. So this is a loss of electrons. I didn't write the word of. So we have a loss of electrons going that way. Anytime we're getting more negative, we have a gain of electrons. That can be a useful little chart to be flipping back to in your notes the first few days. Eventually it needs to be ingrained, or you just write it on your test. So let's summarize what happened. We're always looking for 2 pieces. Okay. We have our zinc solid, or elemental zinc, lost 2 electrons, becomes zinc 2+. So that's our loss. We must have a gain, and we had 2 H pluses. Okay. Each gained 1 electron, so 2 electrons between the 2 of them, and they made molecular hydrogen. So that statement is double compared to my green statement because there's 2 hydrogens. We often have spectator ions. You can have them in acid-base chemistry. We'll have them here. And our Cl doesn't gain or lose. Now we're really going to start studying metals. We're predicting the charges are quite easy. They're either 0 elemental, or we use our table to predict them. With molecules, we've got to learn a lot of new skills. So things like that H2 and HCl, we'll dive in deeper and expand the skills on those molecules in a bit. So we have this gaining, we have this losing. First key definition, the main part of this lesson is to learn, or the main point of this first lesson is to learn the terms that go with the gaining and the losing. So this isn't a math unit, this is a understand, a bit of memorize, apply. So reduction is the gaining of electrons. Anytime you gain, it's reduction. Anytime there's a loss of electrons, that is oxidation. So our hydrogen got reduced or underwent reduction. Our zinc was oxidized in the previous example. When you take these two words, the RED and the OX, you get the name of this type of chemistry. It's redox chemistry. Redox or reduction to oxidation reaction. Okay. These are the subset of all of our reactions where there is an exchange of electrons. And summarizing, so single replacement is always redox. Okay. We'll see that proved to you a little bit more throughout the unit. Double replacements are just exchanging partners. Okay. The pluses and the minus change partners. They don't gain or lose any. We'll see in the future that they're never redox. Now we can write reduction pieces and oxidation pieces, and those pieces we call half reactions. So it's a balanced chemical equation representing either the gaining, so that'd be a reduction version, or the loss, that'd be an oxidation. The two halves in total explain the whole reaction. So we can take this single replacement and write the two pieces. Anything that isn't part of gaining or losing will disappear and not show up in the two halves. So taking our reaction and writing out the two halves. I did the oxidation first. That's not a rule. I just, one had to come first. So that's the loss of electrons. Whenever you're writing an oxidation, I should see electrons on the product side. It's the first thing I'm going to look for. The reduction needs to have electrons being gained, so they have to be on the reactant side. It's one electron for every H, and because there's two H's in the equation, we see two electrons. So we figure things out for one, and then we just scale up to whether we have 2, 3, 4, 7, whatever count we have. So the very top is a balanced chemical equation just like you would have done in Science 10. If I gave you zinc and hydrochloric acid, you should be able to predict the single replacement. In this unit, you should be able to figure out the oxidation reduction, and then we're going to write net redox reactions, where we sum up the two halves, and we have to make sure the electrons cancel out. If they don't cancel, we're going to get them to cancel by finding the lowest common multiple and scaling both half reactions. This first example, we have 2 being lost, 2 being gained. That balances. So we have, there's 2 lost, there's 2 gained. When we net it up, they're going to cancel. No need of lowest common multiple. So the net redox reaction is zinc plus 2 hydrogen ions make zinc 2 plus ions and hydrogen gas. The spectator ion chloride has disappeared. All of our data tables that we're going to use have no spectator ions in them. Okay? And it's nets that we want to often compare back to our data tables. Okay, so how to remember oxidation reduction? Remember what Leo says. Losing electrons oxidized, gaining electrons reduced. You wouldn't believe how many times I say this in my head while I'm teaching to make sure I keep things clear, because I have to have this clear instantly so I can talk about it. I'm going to write Leo and Gur all through my notes to help cue your brain to remember what is reduction. Okay, that's Gur, gaining electrons reduced. They're reactants. They're being put in at the beginning. So we're going to take a look at copper metal and silver nitrate. Products aren't given. This is Science 10 single replacements. We should be able to predict it. We're going to have to predict the Science 10 single replacement. We're going to write two balanced half reactions, and then we're going to write a net that's going to look a lot like the original with spectators gone. So I've pulled down what we would know right from the question. Copper metal, that's just copper, elemental. It's not copper nitrate, copper chloride, just copper, like a brown penny. And that's reacting with aqueous silver nitrate. Silver in our table is a +1 ion, nitrate's a -1 ion, so we need one of each. And I'd like you to think about and complete this single replacement before I write it in. So to get started with answering this single replacement, I'm going to take the copper, which when it becomes an ion is going to be positive, and replace it with the silver that's already positive. So the copper is going to pair up with the nitrate. Now that's not done. I'll come back and fix that. And the silver gets pushed out by itself. Okay? When you have an element and a compound, you always get an element and a compound back. Okay? The order doesn't matter. So to get the proper charge of that copper, you have to remember to flip to your data booklet. So hopefully you did that. You don't have to memorize what the charge of copper is. It's here. It's a little hard to see on the board, but you've got your own table. And the first charge is the most common charge. You don't grab the biggest or the smallest. You grab it by the order. So +2 is the most common charge for copper as an ion. So that's going to be +2 copper. Nitrate is a -1 ion. That's listed on the first page of your data booklet. So I'm going to have to double that nitrate. Now, I didn't look up the state of nitrate. I know all nitrates are aqueous using the solubility table. Silver, all metals are solid except for mercury elementally. Let's look at this. Is it balanced? It is not. There are two nitrates at the end, so we need to get two nitrates at the beginning. That messed up my silver. That's fixable. We now have a Chem 20 Science 10 nice single replacement reaction that we can start analyzing. So I'm going to grab a different color. It really helps to write in all the charges in redox. So you don't have to write in 0 charges, but we're comparing them. I'm going to write them in. So we've got copper 0. We've got silver plus. We've got nitrate minus. I already wrote in copper 2 plus, nitrate minus, and silver is all by itself. It's elemental, like silver jewelry. You don't get shocked when you touch silver jewelry. So we should have a gaining and a losing, or it's not redox. So copper is definitely changing. Copper is going 0 to +2. That's just like our zinc before. It is going up in charge. We're going 0 up to +2, so that is a loss of electrons. So we found our loss, Leo, losing electrons oxidized. Silver is plus to 0. So that is +1 down to 0 is gaining 1 electron. Now there's 2 silvers, and that's why the electrons are going to get balanced at the end. Okay. So 1 copper loses 2, 1 silver gains 1. Nitrate is NO3 minus, NO3 minus, that's a spectator ion. Okay. So we have most of our info that we need to answer A and B. So I have a little bit of a summary, a typical thing. You're going to get asked about what's oxidized, what's reduced. This is the first question on probably your first quiz. Different reaction. What was oxidized? Your brain is going to think Leo, losing electrons. So what reactant lost them? That's copper solid. You must tell me the charge. Okay. The copper plus 2 did not lose electrons. That was the result of. Okay. So elemental copper was oxidized. What gained electrons? That is the silver plus. Okay. If you wrote silver neutral, you're incorrect. That's the product of or the result of reduction. So my 2 half reactions, I'll do the Leo and the Gur. This again is the mnemonic that I keep writing in to help you realize which is which. So we're losing electrons. That's the copper. Okay, there's my loss of electrons. What gained electrons? That's the silver. And we always write half reactions for the lowest common, the lowest possible coefficients. So 1 silver makes elemental silver. Now, I forgot to put the electrons in at the beginning. And as soon as I went to write them at the end, my brain went, that's not reduction. And I put them on the proper side. So these two don't net up. They're just half reactions that represent the 2 processes. So we've answered A, write the 2 balanced half reactions. B is what's the net? So we're going to add these 2 up. We cannot have any electrons in the final net. They have to cancel. Or we're becoming godlike. We're making or destroying electrons, which we can't do. They have to cancel. If we lose 2, we have to gain 2. If we lose 17, we have to gain 17. So our half reactions with the lowest common multiples don't balance. So the lowest common multiple between 1 electron and 2, okay, there's no number here. So 1 is always implied when there's no number. The lowest common multiple will be 2. That's the first repeating multiple. Okay? And that's going to get hidden in our net. So to have 2 electrons on the top would multiply by 1. We don't need to do that. But the bottom half reaction needs to get doubled. So I'm altering the net. I'm now saying 2 silver ions, 2 electrons, and 2 elemental silvers. That 2 electrons cancels 2 electrons. And elemental copper and 2 silver ions will make copper 2 plus. You should not have to rebalance anything. You should get back to the same stoichiometric coefficients that you started with, or potentially sometimes a common multiple scale down. Okay. The spectator ion nitrate is gone. And if I ask you how many electrons were transferred, you can't look here. Your brain goes back to that multiple. It was a 2 electron process. Where we're going with this eventually is talking about batteries and cells, and we'll do a little bit of physics and current at the end with actually knowing how many electrons are transferred. Okay. If we have a power supply, we know how long a battery runs and how much current is flowing through it, we can make chemical predictions. So you would want to practice soon, but some tools to guide you. Number one, you're going to need this table. We looked up copper's charges. Every time you do a single replacement, you're going to this table to figure out what charge the metal has, and you're grabbing that very first charge. Okay. We'll deal with non-metals more later. Okay. But just a reminder of the charge of non-metals. Okay. The noble gases never have charges. Group 7, -1, -2 for group 6, -3 for group 5 when they're ions. Okay. Okay. If you have nitrogen dioxide, that's a molecule. There's no ions there. You wouldn't look up the charge for N and O in that case. Okay. But if you had calcium oxide, the oxygen would be an ion. It'd be a 2- ion. So that's one important tool. Second, you've got a redox table. That's a reduction table. That's always visible for you to see. Okay? So you get a little hint on reduction. If you kind of forget about Leo and Gur, you've got the reduction heading, and then you've got all of these gaining of electrons, or electrons are always at the beginning, so that can help you. Okay? Now we'll talk a bit more about the ordering later, but they are ordered from what most wants to be reduced at the top, fluorine gas, to what least wants to be reduced at the very bottom, lithium ions. Okay. But as you're answering questions and writing half reactions, you'll find the correct version in the table as a bit of a double check and to double check charges. Now you do have these little double arrows. The forward direction is reduction. The reverse is oxidation. So if you answer a question, you write out an oxidation, you want to kind of check, see if it matches what's in the table, you're going backwards in the table from the right to the left.